Thank you to everyone for coming. I am Mirella. I am a geologist for South Arm. In this opportunity, we bring this course to all of you as part of our Deposit Zero to Hero course. We have been organizing these webinars related to ore deposits, cutting edge techniques, and in this time we will present geophysics for mineral exploration. I am pleased to welcome Telma.
Thank you very much, Luz, for the introduction and for the invitation. I'm really happy to be here presenting this geophysics for mineral exploration. And this is the agenda. So I will do some considerations on mineral exploration and general trends on digital transformation, talk about a little bit about the drone revolution, data availability, geophysical methods, a magnetic data workflow, gamma spectrometry, also workflow, gravity and gravity gradiometry, data integration, and a little bit of machine learning. Is is a long thing, but I will try to go quickly on all of this. So this is an introduction. We know that now we can have collect several geophysical methods in just one survey, and this makes us try to extract the maximum from the data. So if we go into geophysics for mineral exploration, the usage in the exploration program or during the mining is a multi-stage and iterative process. The main stages are the definition of the survey objectives, very important. Then you go through data acquisition, data processing, display, and interpretation of different forms of the data. So, and you go on, because if you find some targets, then you do some follow-ups and start again acquiring and processing and interpreting the data. When we talk about exploration, we start with the project generation and area selection. Then we try to have a target generation and then test and this target, and this is a more advanced exploration stage. Then it goes into resources delimitation and reserve delimitation. So this is more for mining engineering. So exploration is from project generation until you have some resources delimitation. Well, it's important to say that it is not easy to find a deposit. So you see here that 1 in 1,000 targets really become a profitable mine. And if you go to a world-class mine, you can say that's 1 in 3,333. So the amount of the gold deposits with enough gold to justify development is about 10%. So it's really difficult. We have to do a lot. But if you have to do, you need a strategy. So you try to have success, you try to work from the known. So you look of the deposit in similar areas. You look at what was already discovered and how is the setting, to go to work from the unknown. And it's important that you can use the historical data that is available and use this for as a vector for exploration. So the past is really risky, but if you use all the resources, it will be better. You will have a better chance to find something. So Uh, it's important that you have a strong team, of course, and a good data usage. So data is really key for this. And if you look at the number of the discoveries, so if we, this is a very interesting report that is available in the internet, and you can see that it is everyone knows that it's harder now to discover more deposits. So the easy ones were already discovered, and this is the what is being used to find this. So you can see that geophysics plays a very important role. And when you talk about geophysics plus geochem, it's really important to use it to find the deposits. And the same at the, this is prospect scale, and this is just like a zoom of this image. And the number of discoveries, as I was saying, um, has been going down, so it's really difficult. And this is an information that half of the all known deposits in the world have been found since 1975. So it's a hard work. And this is number of discoveries by commodity type. You can see gold is very important, as well as iron ore, and by region. So we find here in all regions where we have more discoveries. And here is the number of discoveries. This is smoothed data using our rolling average of 5 years. So it's easier to see. Um and this search method, I think this was at the project scale now. Again, geophysics playing a very important role in those discoveries. So that is very important to use the geophysics. The trends is that we can find some trends. So the location of over discoveries have been made in the last decade. Only 15 from 1,100 discoveries, only 15 were world class. 4 in Canada and China, 2 in USA and Congo, Democratic Republic of Congo, and zero in Australia. So the trends in number, size, and quality of discovery. So gold still remains the main focus. We all know that gold is a really important commodity. And the discoveries were made mostly by the majors. Juniors now account for, no, they used to be driven by the major. Junior now accounts for 65% of all discoveries in number. And the Chinese are, SOEs are important with China. Trends in the discovery. The area selection is mainly driven by presence of non-mineralization, and geophysics and geochemistry are the two main techniques used to site the drill rig to locate the drill holes. And how much has been this? How much has been spent? So, exploration is a boom or bust business. So, the key driver, two principal key drivers are commodity and market sentiment. So, the expenditures are set to rise 32% over the next 7 years. Strongest growth will be in base metals and other. Strongest region will be Latin America and Africa. And the junior companies are now raising cash and are coming out of the hibernation, let's see, and more active in the field. And the best time in the business to an explorer, normally the peak performance precedes peak spendings. So if you spend more, you will find more, and that's the time is always now, because the demand for metals and other commodities are really higher every day. So if we look at the tech trends, so we see that this is an also very interesting report from Deloitte, and the digital experience, the analytics, the data management, this is very important and needs to be applied to the exploration industry as well. Okay, so again, the trends, digital is more relevant than ever. Data underpins the industry's digital future. This is for everything in reality. AI solutions will assist, automate, and accelerate people. The COVID driven change will remain long term, as we are seeing. This is not going to change in short term, and remote operation will drive transition to digital, and sustainability will be a focus for digital technologies. So these are general industry trends, but this applies exactly for mineral exploration. So we need to keep an eye on data, on AI, machine learning solutions, and going digital and remote as far as we can. And this is a slide that I really like and I put in all my presentations, because we need to understand that in the 21st century, we need to have this systemic view for everything. So there is a tale from Indian that says that six blind wise people were going to describe an elephant. And if you put, so one will describe the tail as a rope, and the other with the body as a tree or a wall, the ears as a fan or a spear. So it is very important that you understand the whole thing. And this is also the mineral systems that is being used now, that you need to understand the mineral system, not only the local anomaly, but all that comes with it. This in general, we are seeing this with the COVID, that is very important to pay attention to the environment, to everything that really accounts for what to describe, because the 20th century was based on trying to make the problems easier to solve by separating them, and now we need to put all together. So going back to mineral exploration trends, so we talk about mineral systems. We need to understand, to have deeper knowledge, to understand the geotectonical setting, use all data available, integrating all the data, AI, specifically machine learning applied to data, and we also need to think about a greener and social responsible industry. Those are the really important trends. So before we had this approach to maximize shareholder value, so more focus on operation and less in environment and social. But now we need to, besides maximizing shareholder value, of course, everyone wants to invest and have a return, but we have to extract intelligently and mine responsibly. So we need to take also in consideration not only the operation, but the environmental and social um, responsibilities. So, and we know that we find it's very difficult to find new deposits, but we need to use all data and be responsible. The drone revolution in reality is a new way to acquire data that is being used more and more in the industry. There are lots of common uses for firefighting, for predictive maintenance on power grids, of services of isolated towns and locations, rescue operation in natural disasters zones, and also for mineral exploration. So the UAV MAX systems, for instance, now are really easy to use. They are available. It is a cost-effective, commercially available platform with the development of low-weight magnetic sensors, and also the software development for UAV flight path planning and data processing. So we have all the instruments that can be used, like this Magero, for instance, but there are others, and there are lots of advantages: the efficiency, flexibility, the savings, and the safety. Because in some areas, like in Peru, for instance, it is difficult to fly over such varying topography. And if you compare the cost of ground mag in green, in red UAV mag, and heli mag in orange, you can see that depending on the survey area, it's really cost effective to have the UAV mag. So it compares almost to the ground. But if you grow the size, then the helimag, it's almost the same. When you look at the data, the regional mag compared to UAV mag, because of the flight height, and so the height above the ground, you have really higher resolution, besides also the line spacing that can be smaller. In here, you see how the terrain clearance, it's important to be able to identify and separate different anomalies. This is a work that we have presented in the conference looking into our work that was last month in Chile, and was a comparison between a helimag and a UAV survey over the same area. This work was done together with Carlos Cifuentes from Vale Andina, and Jose Arce from Arce Geophysicists. And you can see that it's really good, and we could show that the results are a lot better, and we could show better resolution of the ore bodies using these techniques. Again, showing the resolution of the bodies. And now, talking about data, I'm talking about Brazil. I'm Brazilian, but in several other countries there are free data. So the Geological Survey of Brazil, CPRM, is providing, freely providing databases from the years 1970 and 1980. And also the newer high resolution, high sampling airborne geophysical survey with magnetic and gamma spectrometric data. This is really good because we can use this data and provide more knowledge from them. So even if we are not with an exploring company, we can generate value from this data and apply several techniques. This is how you can look in the internet and get this data and look at so many geophysical projects in all areas in Brazil. And besides geophysics, there is also other geoscience data available that you can use to integrate. So mineral resources and geochemistry, hydrogeological surveys. There is a lot to explore. And in many other countries, here are just a few examples from the Geological Survey of Queensland that has a really rich data sets there, all types of data sets. Now, also the Botswana Geoscience portal, the Uganda portal, and Australia in general, Canada, a lot of others. Going into the geophysical practice, we know that we start with the data acquisition, the survey design, the field surveys. So this free data also allows us to have better design of the survey. And then we go into the processing, reduction, enhancement of the data, display 1D, 2D, 3D, and interpretation. And now this goes on. So we evolve the interpretation, we bring other data together, we do additional geophysical surveys. So this is the general workflow. And why they are used? They are used in mineral exploration to mapping, to identify geological environments that are favorable to mineralization. And we have 5 different classes of geophysical methods. We can classify them by the geology physical properties. So we have gravimetry and magnetometry for density and magnetization, measuring the variation of the Earth's gravity, and this is wrong, and magnetic field. Radiometry that uses natural radioactivity to estimate the radio elements content in the rocks. And we have seismic that um, allow us to see the variation in the elastic properties from the rocks by observation of the seismic waves. And it's very effective in layered stratigraphy and extensively used in the oil and gas industry, but it is less used in mineral exploration. But as the targets are getting more and more difficult, it is also being applied now for mineral exploration. As we are going to see, it's a more expensive method, but it's really good, the output. We have the electrical methods that are based in the rocks and minerals electrical properties, and it is the most diversified in those 5 classes. So we can measure the electrical conductivity, or its inverse, the resistivity, using the rock's electrical potential difference. We can also use the potentials from natural processes, and the technique is known as spontaneous potential or self-potential. When associated with the injection of electrical current that is passed through the rocks, it's known as the resistivity method. And one extension of the resistivity method is the induced polarization method that measures the rock capacity to store electrical charge. And the electrical properties can also be investigated using the electrical currents created and measured by electromagnetic induction. Those are the EM electromagnetic methods. And depending on the implementation of the technique, other electrical properties from the rocks can influence the measurements, although the electrical conductivity remains an important factor. And we can also classify the methods based in the sources as passive methods that uses natural sources for the investigation, and the receiver measures the response of the local geologist to the natural sources. So those are the gravimetry, magnetometry, radiometry, self-potential, and magnetotellurics. This is very important also because as we are talking about being more friend to the environment, those are methods that really are friendly, environmental friendly. And we have the active methods that uses external sources to input some sort of energy into the earth, like the seismic waves, electrical currents, electromagnetic waves, etc. So the soil response is measured with a detector, and you need both a transmitter and a receiver. Those methods are more complicated and expensive. Uh, Looking from another side, there is also an upside for this, that we can control the results by controlling the source, and we can um, have a specific subsurface information focusing in a region of interest. So if we look for an airborne survey, for instance, we have it going up from the um it goes over the surface, and usually following the terrain when it's possible, it's the better. And the response, when it flies over mineralization, it will show in the profile. The same when you have a transmitter, we'll also read this from uh, your source. And here it is very, very important when you are thinking about what you are looking for, and what is the really good method that will give you an answer for what type of deposit you are looking for. So we can see here that depending on the application, diamond, gold, VMS, MVT, SEDEX, etc., you can use, you have this table that is really good to use for setting up your survey and deciding which methods you are going to apply to your site. This is a similar table. So we have here the source. This is from Michael Dente's book. That is a very good book for mineral exploration geoscientists. And it shows also how the different methods responds to the different types of deposit. So you need to analyze and decide what methods you are going to use. Another thing to think about is, of course, the cost. So if you, this is a graph showing the approximate cost. So this is the cost, and this is the area that is covered. So we see that the gravity, aeromagnetics, public domain are the less expensive method that covers a big area. Also followed by the reconnaissance gravity aeromagnetics, and the more expensive is the seismic. So here I don't think they have the UAV yet. This is but it will be good to also the UAV here because it's a very cost-effective way of spending. And now it's a comparison um, for a drill hole. So the cost compared for the area and the cost for a drill hole. So you can have a fixed wind aeromagnetics radiometrics of 160 square kilometers for the same price as a drill hole. So that's why it's important that you use all the data and try to interpret this before drilling, because drilling is so expensive that it's worth investing in other geophysical surveys before deciding. Talking about the resolution, it's also very important to keep in mind that the line spacing, so the spacing separation between the lines determines the horizontal scale of the geological mapping. So this is the horizontal resolution. And the flight height above the terrain determines the vertical resolution. So this is for you to keep in mind when you are setting up an acquisition. The topography is very important. Of course, flat topography is a lot easier, and the objective, and of course, the cost. Now I'm going to start talking about really what's my specialty. So I'm going to use mag, gamma, and gravity and show some case studies showing the stages of the data processing. So this is a case study from this data that is available. The area is Goiás, Brazil. It's a very important mineral state in Brazil, near to Minas Gerais. Well, I don't know if it's Pará of Minas Gerais, but Goiás is also lots of mines there. So we have used the data, the surface geology from geological survey, the airborne magnetics, airborne gamma spectrometry, and the digital terrain model to generate this. And the geophysical data was acquired in 2004 by Fugro CGG. It keeps changing the names, and magnetometry and gamma spectrometry. The line spacing was 500 meters, flight height 100 meters, and the projected coordinates were SAT 69 UTM 22 south. So here's the data, the ternary, but I'm going to show you the full process for this. So we have taken this data and did the whole process. First, the QA/QC that you need to do while you are flying, because later it will be too late, and you need to have high quality data and look that your inversion really brings you good data. So the QA/QC, you look for the flight height, you look for the line path separation, line distance, sample separation, and the magnetic noise. And you can test for all this and be sure that you have a good data to process and interpret. So then you can go into your database, look into your profiles, also link between the databases and maps, and then you do the magnetic data systematic error corrections. You do the diurnal corrections, you do the lag. So here is how it becomes better and better, lag correction, heading, and then you do the statistical leveling using the timelines. The next step is the IGRF correction. IGRF accounts for the geomagnetic
IGIF?
IGRF, the International Geomagnetic Reference Field, that will leave us with um, the magnetic anomalous field to process and interpret. This is result of micro leveling when you still have noise in your data. You'll use filters to micro level your data. And something very important to keep in mind is that the magnetic data varies with latitude. So depending where you are in the world, you will interpret differently your data. So you use filters, techniques to be able to, like reduction to the pole or the analytic signal, to be able to locate the position of your source. Because you can see here, depending where you are, the inclination, it will look completely different, the magnetic response. And then when you have all your data corrected, you start generating interpretation themes. So you can do it in 1D, doing a 1D analysis. So you can see that you have a dipole here, and you look at the profile of the data. The analytic signal will put everything in positive, so it's very easy to interpret, especially in low latitude areas where the RTP filter doesn't work really well. You use the analytic signal to interpret your data, and then you can do work also into the FFT filters, generating a lot of interpretation. This is the RTP. Then you have the vertical derivative, first vertical derivative, very good for structures. And then you have the second order vertical derivatives. Now you can see that more noise is coming in, but still good to interpret into structures. And then you have the analytic signal. As I told you, it puts everything positive, so it's really easy to find where are the highs. And the tilt filter, also good for structural analysis. And then you can use the radially average power spectrum to determine the source of the magnetic, the depths of the magnetic sources. So this is a classic spectrogram type of analyzing the data using fitting a tangent and using depth estimates. Then you can also use other filters and techniques to do the structural interpretation. And this is the CAT filter analysis, the Euler 3D, the convolution that will give the depth of the, so estimate the depth of the sources. That was a lot used, Euler 3D, but now we have inversion that is available, so it is more used than the Euler 3D, but still easy technique to apply. And you have also other kinds of filters that you can apply in profiles, like the Werner convolution that uses estimates the intrusion and contact and gives the depth of the magnetic basement. And if you do several lines, several parallel or perpendicular lines, you can also grid your data and come up with a volume, a voxel, and interpret your data in 3D. You can do forward and inversion in profiles, so you can interpret each profile and also look at this information like profiles. This is good to match the geology. And as I told you, inversion. Nowadays, everyone inversion is accessible. You have the power to do this. You have the software. So although all the theory is known for many years, now it's
Hello.
really when you have this availability of applying this inversion to your data. So in this area, this is a paper presented, I don't remember, I
Hello.
think it was 2008 in the
Hello.
Geophysical conference. And we have inverted for three targets,
Hello.
Amaralina Marajosa, there are several mineral occurrences in this area, Campos Verdes also, and Santa Terezinha. Então, so these are the mineral occurrences from the geological survey. And just to remember that there is a geophysical ambiguity. So if we have the data and we need to know the model that has generated this data, this is called the inverse problem. The direct problem is when you have the model and you just calculate which data it will generate. So the direct problem is an easy one. You have the model, you know how it is the geology, and you just calculate how the field will appear. But the inverse problem is a very difficult one because in reality, you have many different models that can give the same response. So it is useful to have unconstrained inversions, but if you have other data that can be used as constraints, you have a more real model, because in reality you will find out a model, but you won't know if this is the truth model. So here is the answer from Campos Verdes. And sliding to look, this is a Maralina Marajosa. Also now I'm cutting in depths, looking at the model in depths. And Campos Verdes, I'm looking at the bodies that we think will be the mineralized bodies. So there are lots of ways to looking into the response. It's a volume, so you can extract sections and look into this, and or as bodies using the higher values of susceptibility, looking together with the geology. And now going to the gamma data. Although gamma is a geophysical techniques that it provides information on the natural radioactivity of the elements potassium, uranium, and thorium, and it is a superficial investigation. The depth of penetration is really small, so we'll know about more about this superficial. So it's very good for geological mapping, and it's better considered as a geochemistry in reality as it is. So you apply the corrections to the data, that time, energy, spectrum calibration, background radiation, stripping ratios, depth variation, conversion to the equivalents, potassium percentual, and uranium and thorium equivalent. And then you generate several interpretation terms, like using the total count, the percent potassium, the equivalent uranium, equivalent thorium, flight height, very important because of the mobility of the elements. And you use also the ratios, uranium, thorium, uranium, potassium, thorium, potassium. There is a very good term that can be used, that is the factor F for potassium and uranium, and this is very good when you have Uh, you have different terrains, the anomalous potassium and thorium, and the integrated products. The ternary maps are the better ones, but you can generate ternary maps with all those different themes, and this will be very good. It's good also to look at this in 3D because of the, as I said, the mobility, and to understand better, interpret better your data. So here are some different terms that we generate and can use. This is a zoom, and as you see, this correlates really well with the geology and allows us to have a better geological map. Talking about gravimetry, sorry, we have several reductions to apply to the data: drift reduction, latitude correction, tide correction, correction for the instrument height, and then you calculate the free air bouquet. And also, when a moving platform is used, you calculate the ETFOS correction. It is used for geological mapping, mineral exploration, and geotectonic settings. And you can generate also various interpretation terms like derivative, regional, residual separation, other filters as vertical derivative, total horizontal derivatives, and you can also apply modeling and inversion to this data. So again, you can invert and find your ore bodies, and this is just a Bouquet anomaly map for sedimentary basing, because this is also gravimetry is a lot used in the oil and gas exploration also. So, and we have also the gravity gradiometry, that is a great method also for detecting mineral deposits, especially iron, that you have a really good contrast of the density. And this is important, I didn't mention before. We are talking, when we have all these maps, we are talking about contrast in the physical properties. So this is an example from a gravity survey and a FALCON gravity gradiometry survey. So the gravity ground survey was upwarded 120 meters to be the same as the FALCON GG data that was converted to equivalent gravity. And we can see that it gives a lot more details. We have a higher resolution with these methods, measuring all the components. And I finally come, I think I put too many slides here, but I'll try to go through all of them. My time is almost ending, but I try to go to the end. So data integration. Data integration is key. You have to use all the data you have, the grids, the topography, the inversion models, the models that you've done with wireframing or other geological model, from the drill hole data, all the voxel models. And this is an example of data integration using magnetics and gravity. Will add a lot. And this is a case study from the site of Fugro that is really interesting. That is use the data in a test area covering approximately 800 square kilometers north of Timmins, Ontario. And this is the MDT, the digital terrain model. And there is an open pit here. This is the residual magnetic intensity from this area, first vertical derivative, the AGG vertical component of the FALCON AGG, the GDD, that is the vertical derivative component, the GG vertical component, and the other components that are given by the gravity gradiometry. And then when you compare MAG and GRAV data, you can see that MAG gives a lot of structural information, and you have some correlation, but some not correlated. This is the density contrast, this is the susceptibility contrast, and you can map the surface and near surface geology when you put them use also the time domain EM together with your data, and you can map the bedrock conductor and also cultural conductors here. And using the LiDAR digital terrain model, the surface geology that was published, and putting together with the TDEM interpretation, you can find the magnetic interpretation and the FALCON GG interpretation, when EM interpretation, when you put all these layers together, you can do a much better geological map that was produced by all this integrated geophysical interpretation. So this was the published geology for the area, and now this well, with using all this data, we came with, no, I didn't. They did come with an integrated geophysical interpretation, but this can be mimicked in other places, and that's the idea in reality. To put all your data together. This is a detail to see how much this have added to the understanding of the site. And again, showing a lot more structure, and also the ternary image that can be used with different data. In this case was the first vertical derivative of the magnetic intensity, the gravity gradient, and the dBdt from the TDEM survey. So there are other ways to integrate data. For instance, this is the analytic signal with the tilt derivative, the radiometric ternary data, so you can see the lineaments, the geological and magnetic contacts, the faults. This all happens to find other ways of integrating uranium, potassium with the tilt derivative that gives us the contacts. So you correlate the surface and also the magnetic contacts. And so this is the importance. Use all the data to integrate and give a better understanding of your data. And nowadays, we have also other techniques that can be, so we have this wealth amount of data, and we have also tools to use to do analysis and machine learning to our data. So talking about machine learning, we have both supervised and unsupervised learning. Supervised learning, you have to use a test data set that you train, and then do the classification and also some regression techniques. For unsupervised learning, you can mostly use the clusterings, so you can learn from your data automatically. And I'm showing this. I have been using SOM, the self-organizing map, that is a non-supervised classification technique to analyze and visualize high-dimensional data. And it's a very good tool, an ideal tool to analyze data sets with multiple geophysical parameters, looking for relationship and trends. So it tries from your data, it just uses your data and trying to find the clusters and the classes. So it's an excellent technique. We have applied this, I and my co-authors, my colleagues have used this in several data sets. This is an example from the paper I just presented in the SEG workshop on machine learning, applied to 2D and 3D data. This is 2D. So we have used classification for gamma and mag and the digital terrain model, and came up with very interesting classes maps that will help us understand and interpret the data and find targets. Uh, so the same, we have used also the PCA. So this is the principal component analysis applied to the gamma mag data, and compare this in the middle, sorry, is the PCA. In the left, we have the sum, and this is the normal ternary. And this is Carajás area. We have four magnetic, four geological domains, and we can see that they are clearly seen from this data, and this allows us to interpret better. The same was applied to 3D data. When you invert for the magnetization, you have three vector components, and you can apply some to come out with the magnetic classes. This algorithm also allows us to separate the anomalous classes. So besides giving the background classes, like here, we see them all, and this is just we have we have we are seeing a section also of the data, and those are the anomalous classes. So this really is a very good tool for targeting, because where you see several different classes, those are the most interesting areas of interest, the most targets that you can propose using this. And you can also look at this in profiles together with the geology in a plan map in 3D and other surface information. And here's work that we have used for uh, copper gold porphyry in Canada. So those are the classes. And then we had a higher resolution survey. We did the same with them. We can see that there's a very interesting target over here that we have proposed for further investigation, both in section and in surface. We have proposed this target that hopefully someday someone will explore. And so this is what I prepared to present for you today. I'm open to questions if you have any. Thank you
Thank
for your
you.